So that's what I have at this stage. This is the bottom axis. This is the perpendicular axis. And this is the bed surface, basically. It's a bit thin, but the visa will go on this, so yeah, maybe I change it, maybe not, I'm not sure. It was milled here, obviously, and you know, those surfaces were milled also, and in the middle, of course, here. Everywhere where the rays go, or the bearings, and the rays are 16 millimeters. The ball screws are also 16 millimeters. They have around 28 centimeters of movement in each direction. So yeah, those are 60 centimeters rails, 40 centimeters rails. Stepper motors are the NEMA 23s. So considering the 200 steps per revolution and the pitch of the ball screw 5 millimeters, the resolution should be around 2,500 of the millimeter. There's a need of some clearance here to position rails exactly parallel to each other, so this is why you are using the flat heads instead of centering cone heads. I'm using the flat heads on the bottom. Because this allows for some positioning here. Basically, if you use the cone head, this screw will center the rail in this position. So yeah, basically you need some little wobble here for mounting, just to place it in the right position, to have enough gap to position it exactly parallel to each other. Here it should be loosey, because I'm also using the flat head, but actually they fit through these holes in here, and they're kind of jam in position, so there is not much of the regulation here. Okay, so let me explain. Here is the dial, and it's connected here to this magnet, and this is bolted, on the other side this is loose. So this way I'm gonna set up this rail parallel to the other rail. So that's the setup. We have two stepper motors, two stepper motor drivers for each motor, obviously one. Those are open loop. So it works this way, that you connect, in this case, 4 wires to the steppers. It's in the manual, but you can basically experiment and nothing bad happens as long as the current will be okay. What is crucial, always connect polarity of the power supply to those stepper motor drivers. I will be running them on 24-volt power supply, both at 1 obviously, so that's the thing. Otherwise you will broke the fuse inside, and in case of those ones the fuse is soldered inside, so you won't just remove it easily and change it. The way it works, you send pulses and direction and enable signal. This is from 5-volt Arduino outputs, preferably PWM outputs, and however you send them here, there are dip switches on the side. So this pulse table, first one is 400 pulses per revolution. So on this setup, when you send 2 pulses to the stepper motor driver from Arduino, it will rotate engine by 1 step. So on the next setup with 800 pulses per revolution, 4 pulses are needed for 1 step of stepper motor. So this is why you should connect it to the PWM pins on the Arduino, because they can send signals faster. They are still pretty slow, like 15,000 high-low cycles per second, I think. I need to check it, but the stepper motor drivers can take 200,000 per second in the specification. So yeah, setting them up very high may not be the best idea, but they will run smoother obviously on the higher settings. So the way it will be connected is that pulse negative, direction negative and enable negative will be shorted to the ground on Arduino, and pulse positive will be connected to pulse positive, direction positive and enable positive will be connected to separate PWM pins on Arduino. If there will be PWM pins available due to these TFT shields here. Here are for sure from some communications, but I'm not sure if I can jack into all of them. We'll see. There is the current table on the top also for those dip switches, so it's important. I also have this jog, like from the PlayStation. Can be practical. So this jog is basically a voltage divider. So you connect it to the 5 volts and to the ground, and you can pick this up on the Arduino pins, analog pins, right? And you just translate this value to the position. In the middle it will be around 500, I think, just somewhere in between 1 and 1023, or 0 and 1023. And those are two axes, X and Y. So I can connect them separately. It has resistance of around 1K. So just for safety reasons, it should pull around 5 milliamps of current. So yeah, even if you connect still the analog input, it wouldn't pull really much from the Arduino, so it's safe to use it. So this is the setup with connections made. So the Arduino is here. Yeah, I changed one thing about it, about what I told you earlier. Basically, the enable pin is on. The stepper motor driver is enabled when the enable pin is pulled down. So I basically shorted it down to the ground, and I have shortened enable minus, enable plus, direction minus, pulse minus, on both the same. And those are connected together, and those are connected to the ground of the Arduino. Here's the ground. Yeah, this is the connection to. This is the ground connection to from Arduino to those minuses and enable plus, and those are connected to the other, obviously, either by this cable. And the pulse plus and direction plus cables are connected here to Arduino, to those pins 18 and 19, right? Those will be PWM pins because they are used for the communication. They're actually serial 1 communication, but you don't need to know this. So yeah, and also to another cables with the same principle go to the other stepper motor driver. So those are those two cables, this one and this one, and they are connected to pins 20 and 21. So what else? There is the power supply connected, this wire here, and it goes to the power supply unit. And I obviously measured this with the multimeter. The polarity has to be right. I also connected the joystick. There is the ground connection in here, going, obviously ground, and there is the plus 5 volts. It's this connection here, again to the board, 5 volts, and there are two inputs on the Arduino. So I can read those values from 0 to 5 volts directly to the memory of the Arduino on the A15 and A14. So those are the two axes of the joke, right? Okay, so let's jump to the code. I have coded something before here with the stepper motors. So I have some base code to work with, but anyway, I'm gonna rewrite it and explain everything from the bottom to the top. So you would guys know. I would also open myself, except in the Arduino environment, I would also open the code blocks, because honestly speaking, in the Arduino you can't really find anything if you want many libraries, connections, and so on. So I need to save in the code blocks as .cpp. So or wait a second, actually somewhere in the options, in the editor options, file masks. Star.ino. Okay. And okay. Yeah, so now we have things here highlighted in the code blocks. If you want to find something, you just can, for example, click on something and it is displayed everywhere on the page very clearly and nice. So, you know, that kind of things. So, okay, let's go to the Arduino. So we're gonna define something like steps per foo. We need some variable that will be defining us the number of steps the stepper motor does per unit of distance, right? So, but I don't think we're gonna define it because it should be later editable in the menu. So let's just write and we're gonna do the same for the y-axis, and we're gonna predefine those because let's say, where is the setup? Here's the setup. So yeah, so we're gonna predefine those as for example, for 1600 micro steps settings, we will have pulses per centimeter 3200, right? So 1600 it will be per revolution, but per revolution the screw moves half centimeter. So for the full centimeter that will be 3200 pulses, and the same for the y. Yeah, it could be useful to make them later readable, writable to the EPROM, but yeah, let's for now do it this way. So let's wait with this for later, and let's define all the steppers. And yeah, so stepper X direction, stepper X pulse, and the same with the y-axis, right? So we have direction of stepper 1 at 19. And we have pulse at 18, and the stepper 2 is at the direction 21, and pulse 20. We need some class that will be controlling our stepper motors. So the idea behind this class is a class that will be holding the stepper motor position and will be moving the stepper motor based on whatever the jog input we will get. We will be setting up some speed here for the stepper to move. We will be sending with every main loop the time to this class, and this class, based on the speed that we set before, will be determining if it should make pulse or not, if if those pins should be high or low. So it will also be holding the pins numbers for the direction and for the pulse. Obviously we're gonna start up those classes with those variables here, those stepper motor driver classes. So its pulse, its direction. Well, I'm not sure if it shouldn't be some kind of pointer, but we'll see later. And let's do the same for the y-axis. First we're gonna get time through this function, and we're gonna read the values of the jog. Those were pins A14 and A15. And we're gonna set up from those stepper drivers, right, x-axis and y-axis. We're gonna set up speed and direction based on those here jogs, right, numbers from jogs. And the yeah, so those jogs, they have to be mapped from on positive and negative speed and direction. So let's do some debug stuff. Print those numbers. Jog X and jog Y. Okay, so what from this class stays? Because we basically need to comment almost everything here. So we're gonna leave just okay, so from here we're just gonna comment it, and let's see if it will go through or not. Yeah, so it kind of works. I mean, the class is so first of all, check out what really is here. So we have those two vars, pulses per centimeter that we have defined. We have the pin connections that go into those stepper motors that we will later write this class. This is some remaining, so let's comment it also. And we have just only defined class, some vars that we're gonna change later. And we are defining two objects of those classes, and basically we are just only debugging jog at this point. So we need to have some model of the jog, right? The model is very simple. It has some number in the middle, and it won't be exactly on spot, but it will have some noise. So we're gonna have to figure out how to filter the noise and move those steppers based on the location of the jog, right? Our own feeling of the jog. Okay, so I have Arduino connected with the setup I showed you earlier, and let's upload it, and let's turn on the serial monitor. Oh yeah, I forgot to print line. So those are the numbers in its neutral position, right? Around 495. So the 495 is our middle value. So we're gonna scale this jog. First we're gonna separate this jog. Let's leave like the numbers up from 495 and the numbers down for just noise, and make two cases. If those jogs are higher than 485, right? And then we're gonna map it somehow. And other case, smaller than, well, it should be actually 505 and 485, right? Because the middle is reserved for the noise. And the same principle for the second jog. So we're going to use here the map function. It's described in here. Basically, that's how you write it. Let's write two new variables. And this one will be mapped here, and same thing with the Y. So how we are mapping it, it's we need to map value here from 506. Oh, actually, I'm gonna make it like this. So, Yeah, so we're gonna map value from this to 1023 because that's the max value. The value is being mapped from this thing, right? And now we need our output values. What could be our output values? Obviously from the 0 to, I'm thinking I'm gonna use the numbers, for example, like 500 microns, right? And write based on this thing. This will be our maximum speed of the movement. 500 microns is half centimeter, so 1 rotation per second. We'll see, maybe even more. Let's say even 1000 give it, right? Yeah, so this will be the same for the high numbers here on the y-axis. And now we need to map the low numbers. So the low numbers will be from, yeah, the second part is 2485 from 0 mapped, and we need to map it from minus 1000 to 0. Yeah, so the same will be in here. This. No. So what this is basically doing, it is mapping values from minus 1000 to 1000 on those jogs. So both directions of movement of the jog will be working from our perspective, from our point of view, pretty much the same. So we need to set those two numbers to our classes. So this will be setting speed when the user changes the jog. We also need some function that will be sending time through this function to the to our stepper class, and the stepper class will be figuring how to control the pins, if they should be high or low, how the pulses will work. So this will do through this, and current time micros, this thing here. I changed the int to uint32t because there would be some overflow problems otherwise, obviously. Yeah, I also noticed that the speed x can be obviously negative, so this shouldn't be unsigned int, just normal int 16t on those two. Okay, so let's get into this class. We need to remember the pulse pin, the direction pin, steps per centimeter. This I will explain later. The direction that we are currently moving also could be useful. Last time we did some operation on the pulse. As for reference point, when should be the next one, and the state of this pulse. And we also need to hold the current position, let's say in micrometers. And let's just leave it for now, only those. So how we are starting it, that's the constructor. Basically we are writing those two things, and and also the steps per centimeter. We are setting up the outputs for those pins, for those pulse pins and direction pins, because we will be outputting signal through them. So we also need to have current direction set up as 0. Because we won't be moving at the startup of the program for no reason. And current position in steps. This will later should be read from the EPROM, but as for now, let's just leave it this way. Okay, so to set the speed function, we are basically sending to it here at the bottom in our main loop just one variable responsible for speed per second in micrometers. So depending on this variable, we can set the direction pin on high or on low, obviously, right? So direction can change in few possible ways. One, from positive direction to other direction. So we're gonna be setting this direction pin low in this case. From negative direction to positive direction or no direction, and we'll be setting this, in this case, direction pin high. And the other change of the state is from no direction to positive or negative direction, right? So we need to again change this direction pin high or low depending on this. This gives us every possibility of change in the direction pin. Okay, so now let's write here some half pulse time micros. It should be calculated later, but right now, just for debug purposes, I'm gonna write here something. So if it is supposed to reflect half of the pulse in the microseconds, then for 1000 value, we should really have 500 pulses per second. So this should give us some value to experiment with on the settings presented earlier, like 1600 micro steps on the stepper motor driver. So now in the refresh function, we need to figure out how to make with every half of the pulse change in the pulse pin from high to low and from low to high. So we have this time at check. We know that the refresh function is getting the current time that we got from our main loop. So if we can compare this time to the time when we last did some operation of the pulse and we can add to this time basically this half pulse time micros, right? Compare it to time at check. And if this condition is fulfilled, then we obviously will change our last pulse time for the one that is the new one, right? Add to it this thing. And we're gonna change the state of the pin. And we're gonna add to our counter of the pulses of the position counter, pulse plus or pulse minus, right? So that's relatively that simple. Let's see if it will work. Okay, so nothing happens. And this is obviously quite worrying because the only thing that couldn't work is this thing. We have coded half pulse time micros, hard coded it, right? What is the last pulse time? That's the question. And we haven't defined it here, so yeah, it's always a good idea to define it here as the 0. When the program starts, obviously it will be 0, right? Okay, so I tested it and still nothing happens whatsoever. So let's do if and reverse, right? We actually don't need this one because there are only two possibilities here. Yep. Let's write some debug function here. In this refresh. So we're going to print this timer check. And then we're going to print the state of the we're going to print this thing. So here we can find the reason why. There's like low state, low state, low state almost all the time. Yeah, there's just low state all the time. So this pulse pin doesn't change. I added the new debug in the code. I changed those prints lines to print and added here just some line to print with the print line. Just to check if this condition goes through or not. And here's the output from the serial monitor. And obviously this never go through, even if I manipulate the jog. So this will point that something is wrong in here, in the set speed, in changing of the direction pin. Okay, so mistakes is kind of obvious. I wrote here one equal sign, which is just basically overwriting this into, instead of checking this condition, it just overwrites this variable and returns the condition as the true. So I have noticed a mistake that I've done. It's this thing, just one letter, should be Y instead of X. And I was wondering why I'm getting those strange serial monitor readings. Okay, so now when something finally works, let's go back to the speed function, and we have overwritten the speed micrometers here. So let's delete it. And we know that this should be from -1000 to 1000 with a bigger number reflecting lower half pulse time micros. So let's just do it like this. So if we divide 1000 by numbers from -1000 to 1000, we can get numbers from -1000 to 1000. We can get 0 here. Yeah, the issue is what happens when there is a 0. And the second thing is that it should be ABS from this. It should work. Absolute number, right? And also if the if speed micrometers is equal to 0, we should obviously skip this thing, right? Because we can't divide by 0. And the times also always has to be positive, right? So this refresh function, it just would be stupid if the time would be negative. Then with the every loop of this function, those pins would change its state. And you know what? We don't have the case to change the current direction to 0. So let's have a case in here, because I added this case of current direction equals 0 when the speed micrometers is smaller or equal to 0, right? We are setting the current direction to -1, but actually we should separate this case when the speed is equal to 0 and set the current direction as the 0. I mean, the rest is fine, the rest is good for this. Obviously here similar thing happens, but our current direction pin should be, our current direction variable should be 0. Something is going wrong with this setting up half pulse time micros. So I thought I'm gonna just print this speed and check out what's gonna happen. Yeah, so after printing, I'm getting those strange results. First there's like 0, so that's what it should be. But then when I move the jog, something happens and the numbers that are flowing never go back to 0, despite they should. So because this happens after I initially move the jog, it got me thinking that there is something wrong in here. So it's obviously not written how it should be written in those terms that those analog reads shouldn't be done as quick. The proportion between those calling of these functions, calling of those functions, and analog reads together with all this thing in here, this shouldn't happen in 1:1:1 ratio. So let's do the while loop. In here, and let's just change those proportions in here, because those analog reads should be done one in, like, let's say for example 1 in 20 runs of our main loop. This should happen with every single one, and those should happen together with the analog reads, right? So we need to make a counter. At the end of our main loop, we'll add to the counter. If MLC, actually we can write it in one expression, right? If MLC++ is equal 20, MLC is equal 0. So it will be counting to 20 and back, and this part from here to here, we can move actually this current time micros to the bottom. And here, if our counter is equal 0, then we're gonna do those things, right? So once only per 20 runs. Otherwise, we're just gonna do the refresh function. And at the end, we are zeroing after 20 iterations of this counter or MLC to 0. So let's check this out this way. So that's the number without even touching it. Yeah, and just I touched it and the number swapped so strangely. Okay, so it comes pretty obvious. I use this map function in reverse. So those things should be actually in here, and the same with all of them. I confused inputs with outputs. Yeah, so what is missing in here is the condition when it comes to 0, right? So we have for numbers higher than this, for numbers lower than this, but on the numbers in the middle, nothing happens. So it will hold the latest values that were in there. So yeah, it's consistent with the previous logging experience and so on. So else this thing is equal 0. And the same with the y. So it goes up to 1000. And let's check out the second joke. Oh, it starts from 18. Second. So there's something funny going on in here. Oh yeah, of course. This joke is wrong. So let's take a look at this setup. Because this is what's working at this time. So the control works at this point. Okay, so what else we need? We need, for example, something to calculate its position, to figure out what is its position, and to set up the position to 0. So to set up the position to 0, we will just set this current position pulses to 0. That's simple. Okay, so current position, how can we calculate current position? Let's say in micrometers, right? So in microns, aka. And it should be int 32. Okay, so we know that pulses, we need to make this many pulses per centimeter. Yeah, we need to change those two vars into uint 32t. Or maybe it will be simpler, just int 32t. So to get current position, we just divide the current position pulses by pulses per centimeter, but we need actually pulses per micrometers. This times 10,000 should be in here. On the x-axis. And let's set up those positions to 0. At the beginning. This will be the x and y axis. So I know I will catch you by a surprise, but this thing doesn't work as intended. It should be in 32. In 16t can take up only 232k of numbers. So if this number will be int 16t, then the whole number also will be int 16t, and the maximum, number coming from this will be very low. Okay, so I figured out what is wrong. It's not this expression, it's those pulses per centimeter. In the constructor, we are picking up those pulses per centimeter from this variable here. The problem is that we are calling this constructor in here, right? So this constructor is called before the setup function works. One of the ways is that we could really define those. The problem is that it won't even work if I put it into the setup, right? Put it into the loop somewhere in here. Oh yeah, those are the brilliant things in the Arduino environment. Yeah, now we need to move those things also. Here. And let's see. Okay, so it's time to check. 1 millimeter on the dial, it will be 100, on the screen it will be 1000. So it was just, yeah. Oh, now it's almost perfect on the dial. And here's 2000. So, and so it's like twice that much showing here on the screen. So actually the settings on the stepper motor drivers was 3200. So for this setting, right, this was for 1600 settings, so I should have written here 6400. And now those this current position micrometers seems to fit pretty well. It might be 2 or 3 hundredths off, I mean too high, but that may be because not perpendicular positioning of the dial, right? Okay, so let's write some G1 move approximation function. Actually, it will be a class. So to its constructor, we're gonna give 2 classes of stepper driver, pointers to those classes. And we're gonna give 2 numbers, int32t. It's the final position stepper of stepper 1 and final position of stepper 2. Okay, so this class needs to have some variables. That will be holding those steppers. So let's write something to hold those numbers here. Okay, so let me explain this class. There is the constructor. It takes 2 pointers to the stepper driver class up here, because we're gonna have to control at least its pins and probably some more. So there are 2 pointers to both drivers, right? Because this is linear move between 2 stepper motor drivers. There are finite position in micrometers sent for each stepper motor driver, X and Y for example. And there is the feed rate, micrometers per second, and current time in microseconds. So the idea is that we're gonna, in this constructor, set up this class the same way as we were setting up the stepper motor class with the setSpeed function. And we're gonna have separate function, kind of like refresh, and that will also work based on time. I think you're right. It was checking the current state of the pulse, comparing it with the time that actually is, and determining based on this whether it should change its pins or not. Okay, so this G1 move, this obviously just remembers those two pointers to those classes, and then I calculate the pulses to do by both of those steppers, right? This is basically final position in micrometers times this scaling factor from the stepper motor drivers classes, and there is also the unit thing. It's 10,000 because this unit is in centimeters, this is in micrometers. So there's the 10,000 factor in this, and we are subtracting from the final position, that is absolute. We will be sending absolute position to here. We are subtracting the starting position. And this way we calculate how many pulses to do for each stepper during this linear move. Then we are calculating distance of each stepper to do. This distance is because we can, based on this distance, we can calculate the feed, the speed of change of those stepper motor drivers. This is enough basically to make the move from the beginning to the end, those two pulses to do. But we also need to have some time constraints in here, right? To have the feed reasonable. So we are calculating distance of each steppers that will be made. Fortunately, we have those brilliant functions that we made before in the stepper motor classes, in the stepper driver classes, which are giving us their current position, and we are basically subtracting this from final position that we are sending to our constructor here, G1 move. And then we are doing Pythagoras on this. So with just few words of explanation, because those distance steppers are int 32t, if you raise something to the second power, its number from the perspective of numbers that are based on the multiply of 2 just grows linearly, right? So it's reasonable to write the result of this multiply as int 64. This int 32 wouldn't be able to hold such a huge number so first we need to cast this to int 64, and the second one also we cast to int 64. Then the result of this is also int 64. We do it symmetrically in here for the second stepper, and we sqrt this, and after this we can cast it back to int 32. Those int 64 calculations are so power consuming, so it's the best avoid them everywhere where we can, but here unfortunately. If we calculate also the time of the full move, we would be able to calculate something like half pulse time for both of the steppers, which with analog thinking that we did in the class stepper drivers, right, in this refresh function we are using it. So it could be very good idea to use it the same way. So let's calculate the time for the full move in microseconds. Again, we need some huge number in here because we are expressing this in microseconds. So this is basically the recipe for it. Then by dividing full move time by both stepper pulses, that the amount of pulses that we're gonna have to make, we can get half pulse times for each stepper. And we also do the cast here because this full-time microseconds is in the in 64, which is very time consuming to do operands on this. So fortunately this happens only once in the constructor of this class. And next thing is we are setting the last time that we are setting the time base to 0, right? So from this time where we call this constructor, we will be calculating all those next moves in the refresh function. So for this refresh function, we have those half pulse times for each stepper, and we have amount of pulses to be made, right? So it's kind of the safety thing. Just do this amount of pulses and then stop, and we are sure that we will finish at the right spot. I have written this debug thing to check if it will work. So let's start it up. I'm gonna also show you how I'm calling this function. So this constructor, so x-axis, y-axis, 1 millimeter in x, 0 in y, 10 micrometers feed rate per second. Pulses to do on stepper 1, 640. So for our setup of 6,400 per 1 centimeter, if we're gonna do just 1 millimeter, then it's 640. 1 millimeter. Pythagoras from this and 0 is also 1 millimeter. It will take 100 seconds with the feed of 10 micrometers per second. Yeah, it's 100 seconds. And this is half pulse time. This is 1/13 of the second, right? 78,000 microseconds. So the pulse time from 1/13 will be 1 divided by 6.4, I think, around. So if during 1 second it will move by 6.4 pulses, which will give 100 of the centimeter. Okay, so actually I missed 0 here. So I have noticed something worrying. Is this half pulse time for the second stepper? It's 0, right? This is 0 because we do not do any move actually on this stepper. So to get away with this, as the first thing in the refresh function, there should be a check for those pulses to do, right? And the next thing to do is to check the time. So here we should flip the pulse pin of stepper 1. And there will be it will happen analogically in here. The same with the stepper 2. So it got me thinking that I haven't set up the direction of the move. So, and I should somehow block this stepper, right? We don't want any other moves to be executed, to be messing, especially with our cycle, to be messing with the cycle of the high-low pulse pin. So let's add here in the stepper driver class currently using. And in the constructor, I'm gonna add false. So in here we're gonna log those steppers. We're gonna use this var to log them. So in the stepper motor class, we should avoid using them when this variable is set. So if this is true, we won't do anything, we just return the function, and we're gonna write the same, let's write the same thing in the setSpeed function, because there's no reason to make those calculations, right? So this is explicitly used by some external things, right? Where should be absolute values and where shouldn't be? Yeah, let's do the absolute value after this thing. So and we're also gonna change those pulses to absolute. And similarly with the stepper 1. Forgot to use the pointer to the class of the steppers. Okay, the last thing that I'm worried about is that there should be something to remember the previous direction. So this will save the direction of the steppers before. And to load it, we also need to set up pins correctly. The same for the second stepper. Okay, so this is what we need to do at the end when we figure out that our movement is finished. Okay, so it makes sense to have all this direction pin calculations somewhere around here, because here we are using this pulses to do stepper, and this actually should be in absolute at this stage in here. So this will be absolute. And this, we also have to take care of this full move time, because basically we don't want to take care of this negative values in here, right? It will be simpler if we just write something like pulses to do stepper 1 minus minus and subtract in there. So this thing we know that this is positive, and this one, yeah, by the theory it cannot be negative. Okay, so now in our refresh, we know that this thing will be positive. This thing will be positive, right? So current time minus, if we compare it to those two things, each of those are positive. So now we can flip the pull spin of the steppers. Let's add here in the stepper driver class just function that will flip the pull spins. So last pull state is equal because this is Boolean negation from this thing. So here we can just use this function flip pull spin. And assign new time. Okay, so what if both are 0? We're gonna do this thing. And we need to unfreeze the steppers. Yeah, this is freaking Arduino environment. Can't see anything in here. Okay, so let's change this function refresh. Add here some return value that will tell us if the move has finished or not. So this is where we finish the move. So here it will give us the true, otherwise it will give us false. Okay, so let's create a pointer to this class. And let's dynamically allocate new object of this class. So in our main loop, let's call the refresh function. And let's make bool. We know that this expression it has Boolean value. If it is true, that it means that the movement has finished. So if this thing is true, obviously, then we can delete the current move. I forgot to add time here. Accept destruction of this old object. We should also use this pointer to create a new object. Except we should change those two values, right? So we know just to visualize it better, I'm gonna add here 100, and I think we should get those two values of where from some tables. So let's create some tables. And with the Y, and let's create counter from this class. So our current move counter, we're gonna plus here. Okay, so here's what happens. First, we create the pointer to dynamically declared class. With this is the starting move. Actually, it should be from 0 counter, right? So it will come up with this number and this number. Then we're gonna execute this loop until this move is finished, and we get confirmation from here from the refresh. We're gonna delete this dynamically. We're gonna delete this dynamically allocated object, and we're gonna create the new object with our new positions, X and Y positions, based on those two tables. Okay, so the table starts moving, but both steppers move into one direction, and they never stop, as far as I observed. So let's spit out the pulses to do. In the refresh function, we'll see what's gonna happen. Oh, you're right. So I forgot to subtract here the pulses. That's simple. Okay, so this is strange. It has done like first move correctly, then the second move, third move, fourth move, and after the class was still not deleted because it was working there, so I have no idea why, but that's interesting. Okay, so I have done something stupid. I never finished this counter, right? So this counter will go on. So what it does, it just reads from this array pointer the next position, and there is no next position. There's just some random memory in there. So if this thing is equal 4, if this counter is smaller than 4, let's just do this. So this expression actually should be in here. And it also should be in here, because we can't call this refresh function when we have just left pointer, but the class under this pointer is deleted, right? I rewrote the jog algorithms. Basically, I added here jog sensitivity variable and the middle variable for each jog separately. So they will be later editable in the menu. And there is another issue I have noticed. So this set speed function doesn't get the current time. So there should be some kind of time check. Why? Because there's this variable last pulse time, right? But it's not written in the set speed time. It means that all our calculations are being done as the base point of the time coming somewhere from before. So if this set speed wasn't used for a long time, then this algorithm here will be just adding the half pulse times to this previous early time, right? So it will make the steppers move much faster and possibly dangerous. So this time at check, will be as the last pulse time. Okay, so let's find out where we called this constructor. So it's called in here, so there needs to be added current time macros. Okay, so I created this debug inside the G1 move function because the movement of the bed didn't look correct, and what I'm spitting out is the final position and the get current position functions from steppers and pulses to do. So I got on the serial monitor this result, and it seems like, first of all, get current position micrometers doesn't work, and it always returns 0. I am not using this refresh function. Okay, so let's write some proper buffer for the future parameters of the moves, because basically it's pretty common to first read from, for example, SD card some G code or whatever the source is, write it into some temporary buffer, and then execute command after command after command, right? We need some kind of control mechanism, whether to execute the new move, if there is a new move available, and so on. Okay, so here is this buffer. It is basically this thing. It's table of 30 and 4. Except this, there is this thing actually I'm not using because there's just only one move, one type of the move. So the buffer positions, there will be 30 possible moves written to this buffer. And as this is the buffer, this is the counter for adding the next moves to this buffer, and this is the counter for executing moves from this buffer. So it works this way, that at the beginning counters are set to 0, and I use this add position to buffer to just add positions to its next places. And how this add position function works is that this function determines, based on those two counters, if it is safe to add to this buffer next position, right? Here it just writes the positions, and here it determines, based on those two counters, whether it is safe. So we know that we are starting this with execution and add counter 0. So this add counter could obviously go up to 30 without executing anything. So as long as add counter is, it's a circular buffer, right? So at some point it will want to start to write from the 0 position. It's Boolean, right? So you can just simply return the value that it couldn't be added to the buffer. Here should return true. And it is implemented inside our main loop this way that there's this variable moves has finished. It is in here. We start a tab setup with this variable true. After this check, this execution happens, and basically we are checking if the counters are different. You remember we're starting those counters with 0, 0, like in here. So in every other than their equal situation, there will be some moves in the buffer. So we are just creating a new object of this class based on the positions in the buffer. This is the position X, position Y, and the feed rate here from this buffer to this G1 move class. And we are increasing the counter, and we are changing move has finished to false. When the move has finished is false on the next loop on our next main loop, we are using the refresh function, and we are executing this refresh function until it will come to the situation where it's just ending. So if you remember, we have implemented this refresh function that will return true if this has just ended. So we can use this, and we can instantly, just after this last execution, we can instantly delete the old class, and we can create the new one from new buffer, right? If there are moves in the new buffer, and we are adjusting, obviously moves has finished. So that's how it looks at this stage. It should move on the corners of a square. So first it moves through the sides, to the edges, and then two diagonals. Last three moves are two diagonals in one edge. So here are the positions. Let me show you how to create a menu. So I have this example. I've coded a bit of here. This is part of the menu I have in my project. So it is based on the MCU friend library, which is based on the Adafruit. But MCU friend library has all the serial communication that happens at the beginning of the connection between the driver of the LCD screen and between the Arduino. So it's like kind of a driver library for the touchscreen monitors, small touchscreen monitors like Adafruit 320 pixels or 280 pixels, 240, 380, and so on. And those are pretty nice. They have pretty nice feel, those touchscreens, so that's why I chose one. They're around 15 quid, around. It may be 12, it may be 22, but you know, depending on the size of the screen and some shipment. First, you need to download the MCU friend library. So we are getting it from the GitHub, and you need to extract it into Arduino libraries, and here I have the MCU friend KBV master, and just restart the Arduino and it should be in the examples. And in the examples you need to find MCU friend, and first thing you run is the touchscreen calibration native. So you connect the Arduino, you compile this thing, and you upload it to the Arduino. Remember to turn on the serial monitor. because it will spit out us some values that you will need in your project. So if it doesn't work because there is a file in the MCU friend library that defines support for different screens or drivers or whatever it is. It's this file. It is located straight in the MCU library folder, the CPP file, and it defines support for different screens. So let's just run an example, the most basic example. And as you can see in the setup, you see this is a very simple example. In the setup, there is the identifier variable, and it reads ID from this identifier, and then it prints it out on the screen, right? Or no, on the serial. So when it prints out on the serial, you just need to find this this number somewhere in here. So when you find this number somewhere here, just search for this number in the library, and based on this, there is one of those defines here that may be just commented. The reason why they are commented is because this library writes the support for different screens, for different monitors to the Arduino, and it compiles the support for many screens and sends it to the Arduino. So it includes more support that you actually need during the operation of the screen, but it's in the cost of the memory, right? So as it could work on the Arduino Mega straight away with all the defines probably on, it wouldn't work on the Arduino Uno with all the defines on. So you just need to try all of them. Okay, so with this example, you compile it, upload it, and here is what you will get. This is the calibration screen. And just follow the instructions. So it spitted out here some text, which is basically copy paste, but the same text is also in the serial monitor. And this text is calibration for our touch screen, because it's resistive touch screen. When actually I'm pressing the buttons, it reads the numbers. It reads the voltages from this resistive touch screen, and this way it is calibrated. You see here are those numbers: left, right, top, bottom, and the width and height of the screen. Of course, there can be two calibrations, portrait and the landscape calibration. Okay, so let's get to the menu I prepared a bit. And this is the one. So first there is the include of the Adafruit. Wait, maybe first I show the menu a bit. So this is part of the menu for the XY axis, and it has simple two buttons, two numbers displayed and refreshed with every refresh of the main loop, and two numbers displayed earlier. So here's how it is written. So first there is the include for the Adafruit GFX library. Because the MCU friend library uses the graphics options from the Adafruit, so it's obviously reasonable. And moreover, Adafruits have some ads I will talk about later. Then there's the touchscreen library, there is the fonts library. Those are the pressures for the touchscreen. I think they are somewhere in the calibration, probably. This is the minimum and maximum pressure that you apply to the touchscreen to have the cursor on hold or pressed. And here are those numbers from the calibration. And this is the creating of the new touchscreen object. And here we have the function that is responsible for telling us the position of the cursor and if it was pressed or not. Here's the pressed function. Get XY. You can just refresh it with every your main loop and tell in what condition is the cursor, right? So cursor X and cursor Y will be the cursor positions, and the pressed will tell you if it was pressed or not, true or false, right? So there are some defines of the basic colors. It is displayed this way that first I draw X, Y, I draw the this button, the next button, and with every next display of this part of the menu, I just refresh those two zeros, and I also refresh if those buttons were pressed or not, and I may change the display of just one of those buttons, right? And the same thing happens with every other menu. So in this menu also, I first draw it once overally, and then I just refresh if something was pressed or not. And the same with this menu, I also just once display all of this and then just refresh those two buttons if they were pressed or not. So those displays are being displayed by those draw main menu function, refresh main menu function. This is this menu, by the way. And also I have the draw zero position menu. It is this menu. Refresh zero position menu. Draw control jog menu and refresh control jog menu. So this is this menu. So first I draw this menu, right? So TFT is our object that we created here at the beginning as the one from the MCU friend class, from the MCU friend library. This is the class in there. So we are just creating this screen object. So we have this TFT fill screen black, which obviously just washes our screen to black, every one pixel of it. And then we just set text color, we set text size, set cursor 2015, which will be around here. And we print this message, set current position to 000. And we also print those two buttons. Notice that buttons doesn't have defined place or place on the screen in here. Neither they do not have defined the text size. Overall, everything that defines these buttons, right? Their sizes, also their colors, and so on. And those things are defined in here in the setup. They are declared in here earlier, those buttons. And notice that they are I actually have sorted them according to the menu they belong to. So in case of the set 0 position menu, those are those buttons in here. Those two buttons in here. Yes, no. So those yes and no buttons are then defined in the setup. And they are defined like this. And this is our object of the screen. There's this init button function. It's not a constructor, right? Notice also that they can be earlier declared. So this is the X, this is the Y, which is obviously somewhere in here. Then there is the width and the height, how wide it is and how high. And then there are a few colors defined. And the text in this button. This is highly constrained, the length of the text in this button. It shouldn't be too long. The last thing is the size of the text. Okay, so if we have the button declared, then it is just being displayed by writing this function. It is being drawn, right, by writing this function. And notice that there are two ways of displaying this, as true and as false, which is in the refresh, right? And this display that you see in here is the true one. And when I press it, it will be displayed by a short period of time as the false. So it was just the alternative way of displaying this. When I press it, it will be displayed as the false. Just for a short period, right? You can see it on the every button. And this happens because with every next refresh of the menu, I just check if the button was pressed. You remember this earlier press function? So I can check basically if the button was pressed, because I refreshed this cursor earlier with every run of the main loop, right? Here it is. And then if I find out that the cursor was pressed in this position where this button was, I can just do something. And in this case, I draw the button false, right? So it just changes its colors in reverse. And I also change the menu. Basically, when you press yes, the menu should change back to the primary menu, right? Because it's just confirmation screen for this option. Also on the no, right? But here in the yes, I just do whatever is needed by this button, by this menu that I wanted to do. And I change menu back to the menu 1. This change menu thing has one variable that it relies on. It is called current menu. So in the main loop, notice that I'm just calling only this refresh menu function. And during the change menu function, that after some change in the menu, like it was in the refresh position 0 function, this changes the one variable that is responsible for displaying the current, for remembering which current menu I am displaying. And it always goes with the draw one of the menus as the first time when I'm just switching to the new menu. And with every next main loop, I won't be calling this change menu function, I will be calling this function, right? So this is in every main loop. And notice that each one of those draw menu functions basically starts the same. Here is draw main menu. First, it just turns all the screen black, then it displays whatever is on the screen, right? For the first time, whatever is constant on the screen. So this is constant, x, y. So x is constant, y is constant here. Those two buttons are constant until they are pressed. But the good thing about that being pressed is that they, if you want to change their color scheme, you just throw over those currently existing buttons, right? So there is no need to redraw the entire menu when you are just pressing one button. That will change the entire menu anyway, all over. And then after just printing those constant things in the menu, then I just use the refresh function, which prints the things that change in the menu. So in the refresh main menu function, those will be those two numbers. And how they are printed, there are a few ways of printing it. One way is to, at the beginning of the refresh main menu function, fill this part of the screen in black. So yeah, maybe I demonstrate. To understand it better, maybe I just change color. So now notice that this part of the screen with every one display is just being drawn blue over whatever was before in there. And then there are printed those two zeros. Those are the numbers that I print actually. And before I obviously set the place on the screen to print them and the color of this text. And another way to do it is to quantize actually exact pixels which were drawn the last time the number was displayed, and print them black, right? So yeah, actually I leave this one. And what happens here is that I am printing the same number that was displayed just the frame before, and I am printing it in the color of the background. So as I am printing this in the color of the background, the number stays in the color of the background and is not. And I can print the and I can print the new number over it. Actually, this version it seems slower. So maybe I go back to the filling the rectangle. Yeah, we'll think about it later, but what else? I also have those two buttons that can change those menus to different ones, right? There's the 0 position button and the control jog button. You change menu to 2 and the 4. So this is the change menu, it changes the current variable of the menu to 2 and to 4. And with every next refresh, it will be different menu displayed. So how to start this screen is basically you write it in here and then you define all the buttons and you quantize those buttons to the appropriate menu screens, to the appropriate menu functions, right? And that's the overall trick with it, but you can go further. Actually, in the MCU friend library or in the Adafruit, there's the example where you can input the number to the Arduino. I'm not sure if I have just too old IDE or I don't have just simply this example, don't know why. But there obviously are ways to do it. Okay, so let me show you how this works in this project in the units menu. So we can forget, fortunately, about this negative number function, about this part with the negative number. Here is the number, right? And it is just some global variable. And this number is just being sent through this function here. So I'm clicking it and it's being sent. And here I'm getting the number, I'm displaying all those buttons, okay, and return menu. So here are all those buttons and the number is being displayed. And here are the buttons, right? So what do we have in the refresh input menu? So this is pointed to the function which returns void. Then there is the pointer to the function, and this is the function of 1 int32t. And it also holds I won't get deep into this, but as I started it from this menu, it should also hold this number where to finish after I click OK or return, right? Where to change the menu back. Because this function that it gets in here is the function that sets the variable that needs to be set based on earlier getting the variable from the drawInt32 input function, which was called earlier its global variable, right? This global variable is this one. No, it's this one. This one is the global variable that I'm setting every time I'm calling this, and after this is called, this is being called, right? The refresh function. And so we have something to work on at the beginning. And then all those buttons, what they do is when they are pressed, they do arithmetic math on this number in just simple times 10, for example, plus 1 arithmetics. This is the safety condition in case we overflow this number, right? So it will be higher than int32 actually can take. So all those 1, 2, 3, 4, 5 and so on buttons do arithmetics on this. And then when I press OK or return just changes the menu back, and the OK button uses this function pointer from this variable that this arithmetic math was done at, and is maintained just only by those refresh int32 input function and the draw int32 input function. So this pointer because this is the pointer sent to this function, and this pointer is sent to this function in the refresh x pulses menu. So here it sends this pointer to the function. This is the global function. Here it is, set pulses x. This is the function that connects the many with the stepper classes. So it actually changes the stepper motor class pulses per centimeter variable, and also writes to EPROM and so on. But yeah, that's overall how you connect the many. So let's go back to the mini example, and I will show you one more example. Okay, so this is the jog menu. Notice that when I press it, it refreshes the entire menu, and it draws this button as the false. With the draw function of this menu, I obviously fill the screen black, and then I draw those buttons depending on which option was selected, right? This is the global variable that stores this option. So for every of these buttons, I'm doing the same. And then with the refresh, I can just change this this jog setup variable. Actually, it is changed by set jog2, so there is another function here. But this function actually only does what it does. It only changes this one variable. And in the refresh, there's obviously also the again call to again draw the jog menu, right? Because the jog setup number has changed, so one of those buttons also should change. The entire menu just being redrawn, just for the purpose of getting back this old color of the button. Okay, so that's how it looks with the menu. So there are X and Y values displayed at the top in millimeters. I can move them using the jog. So I can manipulate the jog here. I can change its settings. Here is like a scalar, how fast does it work. Here is the 0.32. One. 3.2. And I have here jog XY currently. Let me write X. See, only one axis works. Y. Only the second axis works. And I move the jog all around. And on the Z, nothing will work. No axis. let's go back here. I can set the current position to 0. I have here yes or no. The camera gets it strangely, but basically here says yes, and on the other side says no. Units, because you see here 6400, so the stepper motors are set up on the stepper motors are set up on 3200 per revolution. So it's the ball screw is the pitch 0.5 millimeter. So I'm setting up this for 6400. Basically, I can change it in here. That's how it looks. 64, let's say. Okay. Now it will operate totally differently. It will calculate the position correctly, right? In different way. So let's get back to 6400. Okay. Okay, so there is the position, there is the units menu, and at the end I have also the G1 move menu. So I can just click on this and I can edit the X, Y, and feed values here and start this move, right? So, but this is in the micrometers. So let's write here 5000, for example. So 5000 will be 5 millimeters. And let's write on the Y 15,000. And okay. Yeah, my fingers doesn't work that nice. My nails, basically, I'm touching it with my nails. And the pen would be much better. And let's edit the feed rate. The feed rate 1000 micrometers per second, right? So 1 millimeter per second. And I press, you have here OK and return, so I press OK. And it's doing the move. 1 millimeter per second. Yeah, so that was it. Okay, so let's check if it will move correctly. I have unit set properly for 6400. And current positions are 9 millimeters and minus 11 millimeters. It's 9 millimeters on this stepper on which I am measuring the movement. And let's do the G1 move. So the X and Y I leave this way, but the feed rate will obviously have to be changed. Let's give it 500. And let's do the move. And I think the ninth one is coming. Yeah, I guess that must be it. But I'm gonna check it once again. I will write the G1 move as the exposition. So let's give it should be able to move 10 and still see on this dial. Just in the right spot. 1, 2, 3, it's in micrometers. And just some Y. And let's do the move. Yeah, so that would be it. Let's change those positions, speed it up a bit. Let's do the minus. $5,000. The other one, let's do minus 1,500. And the feed rate, let's feed it up to 1,200. So that is it. That's with the working menu.